This video will introduce a powerful problem-solving method and one of the reasons calculus is so incredibly useful. Let's talk about rates of change. So you can think of dy on dx, the derivative, as a small change in y over a small change in x. Remember our interpretation of the derivative as the gradient of a tangent at a point. The way we find the gradient at a single point is we find an infinitely small change in y over an infinitely small change in x. And when we find the derivative from first principles, we use a limit to find this gradient. Okay, so another way to think about that is the rate of change of y with respect to x. And this is actually what calculus is all about. It's the study of change and how quantities change with respect to each other. Now, the powerful idea here is we don't just have to talk about y and x. We can use real life quantities like area and distance, or volume, or speed and displacement, or acceleration. And then you can actually use calculus to solve difficult problems. So that's what we're going to be looking at today. I have 3 examples to go through. The first one says a house has a front garden with fence around 3 sides. The total length of the fence is 80 meters. Find the maximum area of the garden. The first thing we need to do here is relate the area to a single variable. So if we call this length x and this length y, we know the perimeter is going to be 2y plus x. So let's say perimeter equals 2y plus x. And we know this is equal to 80. They tell us that. So 2y plus x equals 80. And then we can rearrange in terms of x. So x equals 80 take 2y. Now we can find an expression for the area in terms of y. So let's say area equals xy. And we're going to substitute 80 take 2y in for x. So this is, let's write it as y multiplied by 80 take 2y. And expanding the brackets, we get 80y take 2y squared. Why have we done this? Well, this is an expression we can differentiate. So if we want the rate of change of the area with respect to this single variable y, which was the width of our garden, we can say dA over dy equals, and we can differentiate this expression using the differentiation rules we've learned so far. So using the power rule on each term here, we'll get 80 take 4y. And now we use the same approach we were using when we were looking for stationary points. Remember those 3 types of stationary points from the previous video? They were maximums, minimums, and points of inflection. Here we're looking for a maximum. And the way we find stationary points is we set the derivative equal to 0. So we say when 80 take 4y equals 0, we are going to have a stationary point. And we can figure out what sort of stationary point that will be. I'll point that out in a minute. But let's go ahead and solve this equation here. That's going to give us 4y equals 80. So y equals 20. And this was in meters. Okay, so we have the width of the garden. And why do we know this is in fact a maximum? Well, this is a quadratic. It's a negative quadratic because the coefficient of y squared is a negative 2. So we know that it has this shape. Okay, and a quadratic only has one stationary point. A negative quadratic has one stationary point being a maximum. So we know, in fact, when we found this stationary point, it will be a maximum, and this width is when the area of the garden has a maximum area. So now we can go ahead and find the maximum area using that dimension. So we know that x is 80 take 2y. So plugging in y equals 20, we can say when y equals 20, x equals 80 take 40, which is 40 meters. And then we know the area of the garden, the maximum area is going to be 40 times 20, which is 800 meters squared. Okay, so that is the maximum area of the garden given the length of the fence of 80 meters. Pretty cool, right? So you take a problem that looks quite difficult without calculus, and you can see calculus gives us a nice general method to solve these quite easily. Okay, let's have a look at another example. This says the shape has a rectangular base with a semicircular top. Given a perimeter of 40 centimeters, find the maximum area. Let's firstly find an expression for the perimeter. So let's just call it P. What's this going to be? Well, let's label this length here the side length of the rectangle, x, and we know the base is 2r because it has the same width as the width of the semicircle. So the entire perimeter here is going to be 2x plus 2r, and then the length of the semicircle, which is going to be 2 pi r on 2, or we could just write pi r. So the circumference of a circle divided by 2, which is pi r. And we're told this is equal to 40. As we did in the previous example, we want to write this in terms of x. So let's bring everything over to the right hand side. So 2x is going to be 40, subtract 2r, take pi r. And then dividing by 2, we get x equal to 20, take r, take pi r on 2. Now we can find an expression for the area all in terms of one variable. So the area is going to be the area of the rectangle, which would be 2r times x, plus the area of the semicircle, which is going to be pi r squared divided by 2. And let's substitute this expression for x in here, which will give us 2r times 20 take r take pi r on 2, plus pi r squared on 2, which if we expand this out will give us 40r take 2r squared take, those 2's will cancel, those 2's will cancel, so we just have take pi r squared, take pi r squared, plus pi r squared on 2, which we can simplify further because these are like terms here. So this is like -1 plus a half, right? Negative pi r squared plus pi r squared on 2. So we can write it as 40r take 2r squared, subtract pi r squared on 2. So -1 plus a half is -a half. Okay, so now we have an expression for the area all in terms of r, and we can differentiate this. So we can find dA on dr, so the rate of change of the area with respect to r, which will be 40, applying the power rule to each term, 40 take 2 times 2 is 4, -4r, subtract 1 from the power, and then again, multiply the coefficient by 2, subtract 1 from the power. This will be, well, let's do this over here. So we've got negative pi r squared on 2, and then if we differentiate this, it's -2 pi r on 2, so those 2's cancel. So then we're just left with pi r. Now we have the derivative. Remember, we're looking for the maximum area. So again, we want to find that stationary point. And the way we do this is we set the derivative equal to 0. So we say when 40 take 4r take pi r equals 0, we want to solve for r. So factor the r out from these terms. 40 take r times 4 plus pi equals 0. And then we get a solution for r of 40 over 4 plus pi. 4 plus pi. Again, we should ask the question, how do we know this is a maximum, or it will give us a maximum? It's because, again, this is a negative quadratic. The coefficients of r squared are negatives. So the quadratic will look like this. And the only stationary point it has is a maximum. So we know this will give us a maximum area. And let's go ahead and find it. So we want to plug this r in to the expression for the area up here. Or actually this expression here. Plug it into this expression and we'll get an area. Okay, so plugging in r equal to 40 over 4 plus pi into our formula for the area. It will look a bit messy initially, but hopefully it simplifies down a little bit. So plugging all of this in, take 2 times r squared, 4 plus pi all squared, take pi over 2 multiplied by 40 over 4 plus pi all squared. Let's see what we can do with this now. So the first term, that's going to be 1600 over 4 plus pi. Then the second term will be 1600, 40 squared is 1600 times 2, 3200 over 4 plus pi, 4 plus pi squared. And then subtract pi on 2 multiplied by 1600 again over 4 plus pi all squared. Let's cancel this 2 here. So that will give us 800 in the numerator, 800 pi. And in order to combine these fractions, we want to multiply this first term by 4 plus pi, because these denominators are 4 plus pi squared. So let's go ahead and do that. Multiply that by 4 plus pi. And then we can write it as all over 4 plus pi squared. Okay, so take 3200, take 800 pi. Let's keep simplifying. So expand those brackets out. 1600 times 4, that's 6400 plus 1600 pi. Take 3200, take 800 pi, all over 4 plus pi squared. 4 plus pi squared. And then what do we get? Let's combine the terms, the like terms in the numerator. 6400 take 3200 is 3200. So this is going to be 3200. 1600 take 800 is 800 pi all over 4 plus pi squared. And then factorize an 800 out of the numerator. That gives us 4 plus pi. And we notice we can cancel something further. The 4 plus pi in the numerator cancels with 1 in the denominator. So that simplifies down to 800 over 4 plus pi. Okay, so a bit of algebra to finish that one off. And there we go. That will give us the maximum area of that shape. And that was in centimeters. So that's centimeters squared. All right. Hope you're appreciating kind of how powerful this is. If you think about situations in the real world where you want to find maximum areas and maximum volumes, which is a very practical idea, using calculus really helps in these situations. Okay, the last problem, we're going to look at volume and instead of area. So this question says, 4 squares are cut out of a 24 by 36 centimeter cardboard sheet to make an open top box. Find the size of the squares needed to maximize the volume of the box. I encourage you to pause the video here and think about how you might want to start this problem off. Remember, the aim at the start is to relate what we're looking for, in this case, the maximum volume, to one variable. So can you find an expression or an equation that relates the volume to that single variable x? Okay, let's proceed then. So because we're cutting out a square, the dimensions of the box we know in relation to x. So this length is, if we're cutting out 2 squares, which we're labeling with the side length of x, then this length is going to be 36 take 2x, right? And this length is going to be 24 take 2x. Okay, next we can find an expression for the volume. So the volume of this box is going to be all the dimensions multiplied together. And we know that the height is just going to be x, the side length of the square we're cutting out. All right, so we need a bit of three-dimensional thinking here. So the volume is all the dimensions multiplied together. So x multiplied by 36 take 2x multiplied by 24 take 2x. Okay, and then automatically we have already an equation relating the volume to one variable. And that's the thing you're looking for when you're starting these problems off. The next step in order to differentiate this is to expand out the brackets. So let's expand the double brackets first. Doing a bit of arithmetic, 36 times 24 is 864. Then 36 times 2 take 24 times 2. That's going to be 72 take 48, which is negative 120x. And then negative 2x times negative 2x is plus 4x squared. And then expanding the x out, we have this. And this is going to be a cubic, of course, because we're talking about volumes. Now we can find the derivative. So dv on dx. Applying the power rule to each term, that's 864 take 240 plus 240x, plus 12x squared. Here's another opportunity to pause the video and think about what the next step is that I need to take. If you want to rewind the video and look back at the previous examples at what we did next, maybe that will help. I think it's important to pause at each stage and try to think for yourself what we should do next rather than just listening to me do it. Okay, did you figure it out? Hopefully you said we now need to find the stationary points, which involves setting this derivative equal to 0. So we say when 864 take 240x plus 12x squared equals 0, we're going to get those stationary points. We can divide this whole thing by 12, and I'll rearrange it a little bit. So x squared take 240 divided by 12 is 20, and 864 divided by 12 is 72. So we get this equation, and it looks like we might be able to factorize. Unfortunately, we can't. So I'm going to use completing the square here. So completing the square, we get 8 take 10 all squared take 100 plus 72 equals 0. And then x take 10 all squared equals 28. And then if we take the square root of both sides and write in terms of x, we get x equal to 10 plus or minus 2 root 7. Simplifying that surd as well. So the square root of 28 is 4 times 7, and the square root of 4 is 2. Okay, this is a little bit more complicated than the previous examples because we have two stationary points. This being a cubic, the equation for the volume, that means we are going to get two stationary points, and we need to figure out which one the maximum is. So we need to do a bit of interpretation. Let's firstly go back to our original problem and find out the range of values for x. Well, we know this length here, the shortest length, needs some length, right? It can't be 0. And x can't be more than half of that. So we have a maximum maximum length for x of 12, right? If I make x greater than 12, then I won't have a box. Okay, I'll just cut out two large squares and it will just be a mess. It won't be a box. So we have a maximum length of x of 12. Needs to be less than 12. I guess it could, no, it can't be equal. It has to be strictly less than 12. And it has to be greater than 0. So we have a range for x of 0 to 12. And if we think about this cubic equation, it's a positive cubic, so it's going to be going like this. And we can find the values of the volume at these ends of the interval. So let's draw a quick graph actually. So when x equals 0, this is easy, right? Because every term has an x in it. So when x equals 0, the volume is 0. So if we graph v with respect to x, we know the cubic is going through this point, okay? And if you plug 12 into this expression, you also get 0. So we know the cubic is going to look something like this, going through 0, 12. And we have one of these points in between 0 and 12. So we know that the value in between 0 and 12 will be a maximum. And that's the value we want to take, because any other value of x outside of this range is invalid. And we get one stationary point in this range, and it must be a maximum. So that's how we know, that's how we're finding the value of x to give us a maximum volume. We just need the value of x in that range. And that's going to be 10 subtract 2 root 7, because 10 plus 2 root 7 will be greater than 12. So we know then that therefore x equals 10 take 2 root 7 for a maximum volume, for max volume. And I can't remember if I said I need to find the volume. No, I said find the size of the squares needed to maximize the volume of the box. And there we go. We've found that the dimensions of the squares need to be 10 take 2 root 7 by 10 take 2 root 7. And that was in, what units did I use? That was in centimeters. Okay. All right, so that was a bit of a harder three-dimensional problem. You can see when we go up in a dimension, it gets more complicated because you have to analyze what sort of stationary points you've found, whether it's a minimum or a maximum. But in general, the process is still similar between two-dimensional and three-dimensional problems. All right, there you go. That's a look at modeling with differentiation, sometimes called optimization. It's called optimization because you're finding the optimal areas or volumes for specific dimensions. And again, this is a really powerful part of calculus. And I hope you found that interesting. Please leave a like if you did, subscribe if you want to see more content, and I'll see you in the next one. Bye for now.